Thus, for each epsilon positive, thus for each epsilon positive, there is delta positive, such that for any finite disjoint collection, this AK BK 1 lesser equal to K lesser equal to N of open intervals of open intervals in AB, we have this: if summation K runs from 1 to N, BK minus AK less than delta, then this summation K runs from 1 to N, f of BK minus f of AK with mod is less than epsilon, where this delta, for each epsilon part there is a delta part, this delta is equal to epsilon divided by C. Okay, hence f is absolutely continuous. Hence f is absolutely continuous. Hence f is absolutely continuous. So that means every Lipschitz function is absolutely continuous, but conversion need not be true. We will give an example of a function which is absolutely continuous but not Lipschitz. Okay. Exercise: show that f of x equal to root of x 0 less or equal to x less or equal to 1 is absolutely continuous, but not Lipschitz. Solution: it's absolutely continuous but not Lipschitz. So this I had to show that for each epsilon positive there is a delta positive with this property. Okay, let epsilon be any positive number, and let's take any finite disjoint collection. Let this CK DK 1 less or equal to K less or equal to N be any finite disjoint collection of open intervals in this. Okay, be any finite disjoint collection of open intervals. This interval is 0 1. Without loss of generality, we may assume that this C1 less than D1, D1 less or equal to C2. Okay, so this here is the interval 0 1, we choose C1 is here, then D1 is here obviously, then we choose C1 D1, then we choose C2. C2 may be equal to D1, this is C2, this is D2, C2, and so on. We have then C and Dn. Okay, so without loss of generality, as they are disjoint, we can assume that similar than that's true, that's because it's an open interval, but we can assume that D1 is less or equal to C2, which is less than D2, less or equal to Cn, which is less than Dn. So let's choose the minimum of the lengths. Let m be equal to the minimum of these numbers. Say root of d1 plus root of c1, root of d2 plus root of c2, root of dn plus root of cn. Each number is positive, and this must be a positive number. Okay, let's choose m be the minimum of these numbers. Now we try to find the variation whenever this variation when will this variation is less than epsilon. Okay, now let's find this variation. Let's find this summation k runs from 1 to n mod of f of dk minus f of ck. This is equal to summation k runs from 1 to n. F of dk means the root of dk minus root of ck. But we don't need to apply mod here because dk is greater than ck. Therefore, mod of dk is greater than mod of ck. So it's equal to summation k runs from 1 to n root of dk minus root of ck. Now let's expand this sum. This is a root of d1 minus root of c1 plus root of d2 minus root of c2 plus root of dn minus root of cn. Okay, let's multiplying and dividing by this product. Okay, product I runs from 1 to n root of di minus plus root of ci into root of d1 minus root of c1 plus again multiplying this factor, this term by this number, this product I runs from 1 to n root of di minus plus root of ci into root of d2 minus root of c2 plus continue this process, and finally we have product I runs from 1 to n then product I runs from 1 to n root of di plus root of ci into root of dn minus root of cn, and divided by this product I runs from 1 to n into root of di plus root of ci. Okay, let's the first factor of this product is root of d1 plus root of c1, and root of d1 plus root of c1 is into root of d1 minus root of c1, which it's actually a plus b into a minus b, which is equal to a square minus b square, and that's equal to d1 minus c1. And the second factor of this product is root of d2 plus root of c2, and here is the one more factor, that's root of d2 minus root of c2, root of d2 plus root of c2 into root of d2 minus root of c2, which is equal to d2 minus c2, and finally we have this nth term and this nth Another factor of this product is root of dn plus root of cn, and here is we have one more factor, root of dn minus root of cn, and root of dn plus root of cn into root of dn minus root of cn, which is equal to dn minus cn. Okay, so this is equal so first factor of this product, we club that factor with this factor, so this will give d1 minus c1, and here remain only n minus 1 factors. So I can write it as it's equal to the product I runs from 1 to n, but I is not equal to 1. I is not equal to, not the first factor, root of di plus root of ci, it's plus sign here, okay, into d1 minus c1 plus product I runs from 1 to n, but I is not equal to then this product di plus this root di plus root of ci plus root of di into d2 minus c2 plus the last term, that's product I runs from 1 to n, but I is not equal to n. This is a root of di plus root of ci into dn minus cn, whole divided by the whole product I runs from 1 to n, root of di plus root of ci. But the least number among these numbers, is the m. So I can say this m is less or equal to each factor of this, because m is the least number. You can see here m is the minimum. So m is less or equal to root of d1 plus c1, m is less or equal to root of d2 plus c2, and so on and so forth. So here I can write this is m times d1 minus c1, m power n minus 1, because they are n minus 1 factors, and each factor and m is less or equal to each factor. So this gives m times so this gives m times let me see previous page again. This is here okay, so this is here this is the next. So this one it's this one whenever this is less than epsilon, so this is less than epsilon whenever m times so let's choose let us choose a maximum actually among these numbers. Okay, let's choose suppose m is the max, n is the maximum. Okay, suppose n is the maximum of these numbers, or you can say what will be the maximum of these numbers. That's equal to because each di is less or equal to b, each ci is less or equal to b, so maximum is actually b, so it will be b root of b plus root of b, that's twice root b power n. If I choose maximum here if I also choose the maximum number here m is the minimum, and if I choose capital N, which is equal to the maximum also, if I will choose maximum number also, maximum of these root of d1 plus root of c1, so on root of dn plus root of cn. Okay, if I choose maximum number also, n is the maximum of these So this maximum is, you can see this is less or equal to, because root of d1 is less or equal to b, root of c1 is less or equal to b, so it's less or equal to root of b, because each interval c1 d1 they lie not less or equal to b, they are in 1, so this is less or equal to 1, less or equal to 1 actually. So you can see this they are it's less or equal to 1 actually. Okay, 1 plus 1, that's 2. It's less or equal to 1 actually. So maximum is less or equal to 1, that's trivial. Okay, it's less or equal to 1. Maximum less or equal to 2, sorry, not 1. It's root of 1 plus root of 1, less or equal to root of 1 plus root of 1. So it's less or equal to 1, it's less or equal to 2. Maximum is less or equal to 2 here. So I can say this is less than epsilon. This is less than epsilon whenever m times m power n minus 1 divided by 2 power n times d1 minus c1 plus d2 minus c2 plus dn minus cn, because this one, this m power n minus 1 divided by 2 power n, it's less or equal to this whole, and this is less than epsilon. So whenever this is less than epsilon, so that's I can say. But this one, this is equal to summation f of dk minus ck. So this implies therefore the summation k runs from 1 to n mod of f of dk minus f of ck is less than epsilon whenever this holds, whenever let me check the previous page, whenever this one is less than epsilon 2 power n into epsilon, whenever this summation k runs from 1 to n dk minus ck is less than 2 power n times epsilon divided by m power n minus 1, and that's equal to delta. And we can choose this is 2 power n divided by m power n minus 1. So therefore for each epsilon positive I can find delta positive such that this is less than epsilon whenever this one is less than delta. So that means, that implies f is absolutely continuous. F is absolutely continuous, but f is not Lipschitz. But f is not Lipschitz. For if f is Lipschitz, then there exists C positive such that mod of f of u minus f of v is less than c times mod of u minus v for all u comma v belongs to the interval 0 1. This implies root of u. So let's assume that u is greater than v. Root of u minus root of v is less than c times u minus v. Assume this v is less than u. Assume v is less than u. So we don't need mod here. This is true for all u comma v belongs to the interval 0 comma 1. Now let's multiplying throughout by root u plus root v, root u plus root v. Okay, this implies root of u plus root of v into root of u minus root of v is less than c times u minus v into root of u plus root of v. This is true for each u. This implies u minus v is less than c times u minus v into root of u plus root of v. These two will go. This is 1 is less than c times root of u plus root of v, which implies c is greater than 1 over root of u plus root of v for all u v belongs to the interval 0 1. But by choosing u and v equal to 0, this c is equal to infinity, so that means this c does not exist actually. If they approach to 0, this c will approach to infinity because c is greater than 1 over root of u plus root of v. So this implies this c is equal to infinity. Okay, this is equal to infinity. So thus this f is not a Lipschitz function. F is not Lipschitz function. Next we have a theorem the theorem is let the function f be absolutely continuous on closed interval ab. Let f from ab to r be absolutely continuous, be absolutely continuous on closed interval ab. Obviously it's a function on that interval. Then f is difference of f is the difference of increasing absolutely continuous functions. Increasing absolutely continuous functions. In particular, f is of bounded variation, because whenever function f can be expressed as a difference of two increasing functions, then it's a bounded variation. And in particular, this f is of bounded variation. In particular, f is of bounded variation. So that means we are actually showing that every absolutely continuous function is of bounded variation. Obviously, converse is not true, because there are functions which are not continuous, but still they are bounded variations, and any function which is not continuous is not absolutely continuous. Okay, let's prove this theorem first. Proof. Let let f is a function from ab to r be absolutely continuous, be absolutely continuous. It's already in the statement actually. I would need to mention it here, but for you I am mentioning it again here. Let this function be absolutely continuous. Okay, we first show that f is a bounded variation. we first show that we first show that this f is of bounded variation. We first show that f is a bounded variation. So first, since f is absolutely continuous, therefore for each epsilon positive, we can find delta positive. So for since f is absolutely continuous, therefore for epsilon positive equal to 1, for each epsilon positive, in particular for epsilon equal to 1, it is a positive number. There exists a delta positive such that for any finite disjoint collection ck dk 1 lesser equal to k lesser equal to n of open intervals in a b, we have this if bk, sorry, it's dk, if summation k runs from 1 to n, dk minus ck less than delta, then summation k runs from 1 to n mod of f of dk minus f of ck is less than 1. Epsilon is 1 here. So for epsilon is equal to 1, there is delta positive. So I have fixed this epsilon, okay? I have a delta for this epsilon positive because f is absolutely continuous function. Now let p be any partition. Actually, we had to show that f is a bounded variation, so that means we have to choose the partition. Let p be any partition. Let p be a partition. P be a partition of AB into capital N closed subintervals is divided into be a partition of AB which divides interval AB into closed subintervals, closed capital N closed subintervals, it's a ck/dk. So this is a ck/dk, okay, 1 lesser equal to k lesser equal to capital N, okay. This is C1, D1, C2, D2, so on and so forth. This is the part. These are actually partition points of this interval A, B, such that the length of each subinterval, let P be a partition of AB into n closed subintervals, which is partitions into n, dividing this interval into n subintervals, such that length of each partition, length of each subinterval, such that length of each subinterval is less than delta. is less than delta. If the length of each subinterval is not less than delta, we insert more points, and we know that under the refinement the variation is increasing, not decreasing. Okay, which is more partial. Later we show that this variation is finite, or total variation is finite. Total variation is finite. Okay, such that the length of each subinterval is less than delta. Less than delta. Then, if the length of each subinterval is less than delta, then what will be the variation? What will be the variation? What will be the total variation of the function f over the interval ck dk? What is this total variation? Or what is the variation over this interval? First we find the variation, okay, with respect to any partition. So let me first write this. Okay. Then this variation of f over the interval ck dk with respect to any partition, let's denote that partition by p dash or p1, where p1 is any partition of the interval ck dk. Since the length of the interval ck dk is less than delta, therefore if we choose any partition, the sum of the lengths of all those intervals will be less than delta. But whenever the sum of the lengths of the interval is less than delta, then the variation over those subintervals is less than 1, because f is absolutely continuous. And here you can see it. Whenever the sum of the lengths of the interval is less than delta, then the corresponding variation is less than 1. Okay. So here the lengths of the subintervals of ck dk, lengths of subintervals, sum of the lengths of the subintervals of the interval ck dk is always less than delta, because the intervals are disjoint here. So that means if whenever the lengths of the sum of the lengths of the subintervals is less than delta, why it's less than delta? Because total length is less than actually delta. But whenever the sum of the lengths is less than delta, then the corresponding sum of the function's variation is less than 1. So this means it's, and this is the variation actually. You can see this is say if you choose the partition, say x0, x1, so on up to xn, then what is this variation? It's equal to mod of f of x1 minus f of x0 plus mod of f of x2 minus f of x1 plus so on up to mod of f of xn minus f of xn minus 1. But that variation is always less than 1, because the sum of the intervals, sum of the lengths of the those intervals, say x0, x1, x2, so on up to xn, these open intervals, the lengths of those, sum of the lengths of the open intervals is less than delta, because the length of the total interval ck dk is less than delta. So that means this is less than 1 for any partition p1. For any, say, let me write this as pk, for any partition pk of this kth subinterval ck dk. So if you choose a maximum, or you can say the supremum, that means total variation of the function f over this interval ck dk is less or equal to 1. Okay, so this means this implies the total variation of the function f over the interval ck dk is less or equal to 1. Fine. Okay. Now what's the total variation of f actually? Now the total variation of f over the interval a, b, and this is the partition. So these are the subintervals of this. So it's equal to summation k runs from 1 to capital N, total variation of f over the interval ck dk, okay, over the interval ck dk, and each is less than 1, and it's less than 1 plus 1 plus 1 n times it's less or equal to 1 plus 1 plus capital N times, that's equal to capital N, which is finite number. So that means total variation is finite. So this implies f is of bounded variation, and hence f can be written as difference of two increasing functions, and hence this f is equal to g minus h. What's this g and what's h? Where g is equal to f of x, g of x is equal to f of x. It is in that theorem, Jordan decomposition. G of x is equal to f of x minus the total variation function of f over the interval a to x, and this h is equal to total variation function f over the interval a to x, where these are, this is h of x, are increasing functions. They are all are increasing functions, Okay, so this f can be written as difference of two increasing functions g and h, where this g is equal to f of x minus total variation x, and h of x is equal to total variation ax. Okay, so this is but we have to show that this f can be written as difference of two increasing absolutely continuous function. This f is given to be absolutely continuous function, therefore it is we have to show that g and h are absolutely continuous actually, but our f is given to be absolutely continuous function. So therefore it is sufficient to show that this total variation is absolutely continuous function, because the sum of two absolutely continuous functions is again an absolutely continuous function, and difference is also. So that is an exercise for you, and you have to show that the collection of absolutely continuous function is closed with respect to the addition and the scalar multiplication, from which you can easily get this. If the difference of two absolutely continuous functions is again an absolutely continuous function. So therefore it is sufficient to show that this total variation function is absolutely continuous, because if you will prove this total variation function is absolutely continuous, f is absolutely continuous, the difference is also absolutely continuous, so that means g is absolutely continuous. H is also, because h is the total variation function. So but now we need to show that g and h are absolutely continuous function, but we need to show that g and h are also absolutely continuous. It is sufficient to show that it is sufficient to show that total variation function t a to x is absolutely continuous as the collection of all absolutely continuous functions is closed with respect to pointwise addition. The addition is pointwise addition and pointwise scalar multiplication. Pointwise addition means f plus g of x equal to fx plus gx. Pointwise addition and pointwise scalar multiplication pointwise scalar multiplication alpha f of x equal to alpha times f of x. Okay, so it's sufficient to show that total variation function is actually absolutely continuous. But how do we do that? That total variation function is absolutely continuous. So let epsilon be any positive number. I have to find delta positive. Okay. Now, since f is absolutely continuous function, we have a delta positive, which is for that function f. Choose delta positive as a response, as a response to epsilon by 2, as a response to, because for each epsilon positive I can find delta positive. For I choose epsilon as epsilon by 2. Choose a delta positive as a response to epsilon by 2. Challenge regarding the criterion for for f for the function for the absolutely regarding the criterion for the absolute continuity, for the absolute continuity of f. So because since f is absolutely continuous function, therefore for each epsilon positive I can find delta positive. So let's choose epsilon as epsilon by 2. So for this epsilon by 2 I can find delta positive, which for this this epsilon by 2 and this delta positive, they work for the function f. Okay, because f is given to be absolutely continuous function. So choose a delta positive as a response to epsilon by 2. Challenge regarding the criterion for the absolute continuity of f. Okay, so that means whenever we take any finite digit collection of open intervals such that the lengths of those intervals, sum of the lengths of those intervals is less than delta, then the then the variation of the f over those intervals is less than epsilon by 2, as f is given to be absolutely continuous function. But we need to find delta for total variation function. For f it is there because f is absolutely continuous, but we actually need to find that delta for total variation function, and we will see that same delta works for total variation function. Okay. Now let's choose any finite digit collection of open intervals such that the length of the subinterval is less than delta, and we show that the variation of the total variation function is less than epsilon. Okay, let this be the intervals. These be the open intervals ck dk 1 less or equal to k less or equal to n be a disjoint and finite collection, be a finite disjoint collection of open intervals in A, B, such that the sum of the lengths of the open intervals is less than delta. Is less than delta. We show that the variation of total variation function. We show that summation k runs from 1 to n. It's monotonic increasing total variation function, so we don't need to write mod here. We write the total variation of the function f evaluated at the point dk okay, minus total variation of the function f evaluated at the point ck. Okay, it's actually like this, t of dk minus t of ck. Okay, where that t is the total variation function. We show that this one is less than epsilon. Okay, this is less than epsilon. We don't need to apply mod here because the total variation function is monotonic increasing and dk is greater than ck. Okay, so this is what we need to show actually. Okay, we need to prove this star actually. So it's now this sum is less than delta here. So how do we do that? First, for 1 less or equal to k less or equal to n, we have these and open intervals. Let's choose a partition of each interval. Let pk be a partition of the interval ck dk. But the sum of the lengths of the interval is less than delta, therefore the length of this interval is also less than delta. So therefore the lengths of the subintervals of this interval ck dk is also less than delta. And by choice of delta positive, in relation to absolutely in relation to absolutely continuity of f, on AB, we have this summation k runs from 1 to n variation of the function f over the interval ck dk with respect to the partition pk is less than epsilon by 2. Because if you add these variations over the interval c1, because total sum of the lengths of the intervals is less than delta, so if you choose any partition over the interval c1 d1, say p1 over the interval c1 d1, p2 over the interval c2 d2, so on and so forth, then if you calculate the sum of the lengths of all subintervals, first you take the sum of the intervals of, say, the partition, we have a partition p1 of c1 d1, so we have certain subintervals, we add the lengths, then we add then we take the partition p2 of the c2 d2, and we again add the intervals, okay, subintervals, and we'll see the total length. This it's actually sum of the sums. First you take the partition p1 of the interval c1 d1 and you add those lengths of the subintervals, then you take partition p2. So suppose that addition is equal to say it's equal to some constant, say it's equal to say c1, then you take the partition p2 of the interval c2 d2, then again you add the lengths of the subinterval, suppose that sum is c2, and so on. You do it for each subinterval, and then you add those c's, c1 c2 up to that sum is always less than delta, because the sum of the lengths of the interval ck dt, sum of the lengths of the interval ck dk is less than delta here.